1.3 here, pre-calculus. You should be on page 7 of your packet. What we're going to do today is talk a little bit about domain again, finding domain, but then start getting into when a graph is increasing, decreasing, and when it's at its maximum or minimum points. All right, we've got the graphs here of these two relations. If every vertical line meets the graph of a relation in at most one point, then the relation is considered to be a function, What we want to do is look at, again, the vertical line test. Is it a function, yes or no? So you run a vertical line through your graph at any point. Well, this one obviously is intersecting it twice, here and here. So no, this is not a function. All right, if you run your vertical line through here, the sine curve or cosine curve here, yes, this is a function. Every vertical line just intersects one, so yes. That's a quick review of the vertical line test. Finding domain. So find the domain and range. Range now would be, so your domain is the x, and the range is your y. First, we're going to do it algebraically. Algebraically, let's look at my original function. I've got a square root, so this expression here, algebraically we would go x plus 1 has to be greater than or equal to 0 because of taking the square root, and you need a positive result. So x would be greater than or equal to -1.
Pardon this interruption, teachers.
All right, so then our notation that we're going to use is from -1 to infinity. Okay, now the graphical solution. What does this look like? Let's see if we can get our graph here. All right, I went ahead and for this lesson here, I've put into my y equals all of the functions that we're going to graph. So in y equals y1, go ahead and graph the square root of x plus 1. And so this is what it would look like. So visually, what is my domain? My domain, let's see, the graph starts here at -1 and then continues to the right. So then you can see that what the graph looks like compared to what our domain is. Okay? So my x and y axis, -1. It's the furthest part of your graph, and then it goes like that. Okay, so still we have the same domain, whether we found it algebraically or graphically. Okay? All right. Example 2b. Find the domain and range of the square root of 9 minus x squared. Graphically, we will go back to the graphing calculator, but algebraically we're going to take the expression. Since taking the square root, it has to be greater than or equal to 0, non-negative, then -x squared has to be greater than or equal to -9. So then x squared has to be less than or equal to +9, because this was a negative. So x has to be less than or equal to plus and minus 3. All right, so what we're going to need to look at here is where's this true and where's this false? We got two solutions, a -3 and we got a +3. Okay, so let's think about if I put in, let's say I put in something in between those. We already know that 3 and -3 work because you would get the square root of 0. If you put both 3 and -3 in here, you get 9 minus 9, which is 0. Those are okay, but what about between them? So let's put 0 in. If you put 0 in, 9 minus 0, we can take the square root of 9. So this is all true in here. And -3 was okay. And +3 was okay. What about things to the outside? So what if I put in 4? Square root of 9 minus 4 squared, that's 16. That's not true. This is false on the outside. And if I put in -4, you still get the same result. -4 squared is 16. So this is false. You can see here my domain is in between. So we can do x falls between and including -3 to +3. Or we can do bracket -3 to +3. Like that. There's your domain. All right, now let's look at the graph of it. So go to your y equals. Let me go ahead and turn this first graph off and turn the second one on so we can see it. There you go. So you can see that this curve exists between -3 and +3. This is what it would look like. It's a half circle is what it is. Looks like that. So again, the domain is the same, -3 to 3. All right, so that's how you can do both algebraically and graphically, finding your domain. We didn't talk about the range. Let's go ahead and go back to that first example and talk about the range. My smallest x is -1. Well, if my smallest x is -1, then you get the square root of -1 plus 1, which is equal to the square root of 0, which is equal to 0. That means this is the smallest y that comes out of it. Okay, so my domain was listed, and now my range. My smallest range, the smallest value that you can get when you take the square root of something, is 0. So from 0 to infinity. Okay, looking at this one, same concept. You can just look at the graph and you can see it's always above the axis. So the range is from 0 to infinity. Both cases. In fact, I think sometimes it's easier to look at the graphs, but it's important for us to know how to do it algebraically. Where does this, what does this give us? If you're taking the square root of something, the smallest y value that you can get for the output would be 0. So again, this was our domain for both of them. So my range would be from 0 to infinity. Well, actually, not going to be to infinity because if my smallest x that I put in here, maybe you can see it here from the graph, but if my smallest x that I put in here is 0, then the square root of 9 minus 0 is the square root of 9, which gives us 3. So really, the largest value that we can get is 3, because as soon as we put in something to the other side of the 3 and -3, we're going to get negative square roots. All right, so the largest value is 3. So you can see here that my graph starts at the origin and goes all the way up at a maximum of 3. We're not going to get anything larger than 3 coming from that square root. All right, increasing and decreasing functions. A function f is increasing on an interval if for x1 and x2 in the interval such that x1 is less than x2, then the function of x1 is less than the function at x2. Here's what that means. If your graph is increasing, it's going up like that. That's an increasing. Decreasing is the opposite. This would be decreasing, going down. It can be linear. It can be at a curve. Okay. So if x is less than x2, but the function of x is larger at 1 than it is at x2. And we've got one other one. It's a function is constant. So when a function is constant, it's because in that interval it's horizontal. Okay, so they're equal to each other. The functions are. What I'm going to do is show you an example and kind of map out. If I give you this as my graph, here's what I can do. Is I can show you that between the beginning of my graph and here, Okay, this is increasing. And then between here and here, between the top vertex here and this point there, this is decreasing. The graph is decreasing. In this region, it's constant. And we're decreasing again. So it's all about when it changes directions. It's decreasing here, now finally it's increasing on the far right here. Okay, so we're going to look at when is a function increasing or decreasing over an interval. So you should now go to page 8 of your packet. Here's my graph. Determine the open intervals on which f of x equals x to the third minus 12x. Determine the open intervals. Basically, we were trying to decide when is it increasing, decreasing, or if it's ever constant. Well, so your graph starts coming from negative infinity. It's going all the way up until this point right here. Okay? So we got a change in direction here. So we've got, it's increasing on the interval from, so here we go, increasing from negative infinity all the way up to, and so we would need to know what that vertex is. Okay, you guys can do this. Okay, if we go to our graph, actually what we need to do is we need to find the vertex for both of these. We're going to do it at the same time. Okay, because in this region, the graph is decreasing, and then it's over here increasing again. So we just need to figure out what is the x value here and here to decide which region we have for increasing and which for decreasing. Let's go back to our graph. All right, so here I'm at my graph, and I did change my window. You can see here my window on my y min and y max. I put them from negative 20 to positive 20 so that I could see the graph. You have, go ahead and put it into y equals, the full function, and you can see here that it looks like at negative 2 I've got my maximum point. At negative 2 maximum, okay, here's how you calculate it. You go second, calculate. This is a maximum point. And then you move the cursor. Move the cursor over to the left side because it's asking you the left bound. Hit enter, you go to right bound. Hit enter, and the third time, guess, that's when the calculator will do it for us. So you can see here negative 2, maximum is 16. So this graph is increasing from negative infinity to negative 2. Okay? And it's also going to increase in another place. So let's go ahead and go back to our graph and look at the next interval. All right, so we now need to find the ordered pair on the other side. So you go second, trace, arrow down to max. Actually, this is going to be a minimum point. And you calculate that. So you move your cursor till you get closer to your vertex. Go left bound and then hit enter. You go to the right side. Enter, and the third time is to calculate it. So it looks, it's like 1.999, that is 2. So my graph is decreasing from negative 2 all the way to positive 2, and then it's increasing again from positive 2 to infinity. So we can use that vertex here, this vertex right here, as a change where it goes back to increasing again. Okay, that's showing and looking and using your vertices, the vertex, the max and min points to figure out the intervals at which your graph is increasing and decreasing. All right, f of x equals x to the third. This is our function right here. We don't need to go to the graphing calculator. Think about your table of values. As x comes from negative infinity, so that's where it's coming from, negative infinity, and it goes to positive infinity. And at no time does this graph ever change the fact that it's slowly increasing. Okay, I know it starts to flatten out here as it gets closer and closer to 0, but if you substitute points in here, like substituting -1 in, if you substitute -1 in, you get -1. If you substitute 0 in, you get 0. 1 is +1. It's slowly increasing. You'll never have a y value be the same at any point. So this is increasing over the full interval all the way. Okay, not decreasing at any time. All right, let's look at the one more here. This is our graph of this piecewise function. We've got t plus 1 for t less than 0. This is an open circle. Then we've got a horizontal line until we get to 2, and then we've got -t plus 3 for the second. So this is our piecewise function. It's graphed. And let's look at, where is it increasing? Well, here's increasing. Okay, so from -infinity all the way to 0, increasing. -infinity. That was bad. To 0. We don't ever use like brackets. It doesn't include 0. It's just going up to that point. It's staying constant. Staying constant from 0 all the way over to 2. And then now it's decreasing from 2 to positive infinity. There we go. So you basically take each of these parts and you write an interval in notation here, interval notation, in order to get all of the parts, the increasing, the constant, and then the decreasing. All right, the last thing that we have to talk about is relative minimum and maximum values, which we'll use the calculator to find. A relative minimum and maximum is a relative minimum of the function exists if there exists an open interval I containing a such that f of a is less than or equal to f of x for all x in I. Okay, let's just talk about what this means. A relative minimum. A relative minimum would be when you have a graph come down to a minimum point and then go back up. So it's basically, it's when you change from having a decrease to an increase. This would be a relative minimum. And so you can see a relative maximum would be this. This is a relative maximum. So f of a, this is f of some point a, is a relative maximum of the function f if there exists an open interval I containing a such that f of a, so this is the most of that function right there. F of a is greater than the function for all x. All right, to find it, what you do is you put these in your calculator and you go ahead and calculate the vertex. Okay, let's look at what this one would be. I have both of these last two entered in my calculator. I'm just going to go to Zoom 6 to start out with. Remember, Zoom 6 takes us back to our original. Let's go back to y equals. I'm going to turn that one off. Now we can graph it. All right, so there's your graph. I went ahead and into y equals, and you would type your function in, and then you're going to do Zoom 6, making sure you get a nice window for it. Now we're going to calculate that relative maximum. So you go second trace. The maximum is number 4. And you scroll to the left side of it. You hit enter, You scroll to the right of the vertex, you hit enter, and then the third one's guess, and that'll take us to it. So this one we've got negative 0.3 repeating, which is negative 1/3. And then we've got 1.3 repeating, which is 4/3. So negative 1/3, 4/3 is the ordered pair. Negative 1/3, 4/3. This is the ordered pair at which the maximum occurred. Okay, last problem. The profit for a new company can be modeled by this function. Go ahead and put that into y equals. It says P is the profit in thousands and X is the number of units sold in thousands. What would be the maximum profit for this company? All right, go back to my graphing calculator. And we're going to pull up this graph. I'm probably going to adjust my window a little bit so that I can see it. It's in thousands. I don't know. I'm going to start off by going, if you go to your window and you set your domain up, let's go from 0. Let's start 0 to 20, and we'll just do zoom fit. Zoom fit is if your domain's set up, then it's going to give you the graph or what you need for your graph. So there's zoom fit. Well, we at least see our maximum up here. Okay, I'm going to go and change my y's a little bit so that I'll be able to read the vertex. So my y maximum, I'm going to go ahead and go up to, looks like it's going from 132. I'm going to go to 3,000. Just want to change the shape of it. All right. So there's my expression, and it's showing me my maximum here, my maximum point. So you do, we go second, calculate. Maximum is number 4. And we're already to the left of the maximum, so hit enter. You do left bound first. The calculator takes you through this procedure. And then right bound, make sure you're to the right of the vertex, and then the third one's enter, and it's looks like it's 11.95 or so. Okay, and then we've got 1822. So this is my maximum point, 11.9, which is about 12, and then 1822.6. All right, so here's what we've got. We've got 12, comma, 1822.6. It's 0.68. Okay, so what does this mean? What is it asking me to do? It says, what would the maximum profit be? So it's 12, so about 12,000 units. So the profit would be 1,822.68. Okay, there's your final answer. All right, that's how you find out relative min and max, and we did a little bit with domain and increasing and decreasing today. This is your assignment.